Okay, so we move on to the next speaker. It's Clifford Cheung, and he will continue to talk about the soft theorems and other things.
Okay, let me first start by thanking the organizers for putting together this wonderful conference and for inviting me to speak today. I've had a fun week. I can tell that the audience may be wilting a little bit, so I'll try to minimize the brutality of my talk. What I'll tell you about is some work kind of in progress and work completed with my collaborators Anton De La Fuente and Raman Sundram concerning something that's kind of at the crossroads between scattering amplitudes and holography. So before I jump into things, maybe I should just set the stage a bit by telling you the original impetus for this work, which was a series of incredibly interesting papers by Andy Strominger and collaborators concerning asymptotic symmetries of flat space and scattering amplitudes. So if you haven't seen these papers, I encourage you to look at them. There's something very interesting going on. At least when I saw them, I don't think I absorbed everything completely. They're kind of dense in some places, but definitely something interesting is happening. I won't kind of repackage all those statements, but let me kind of distill at least what I gather to be the salient points. The claims of Strominger are twofold. The first is that there exists in flat space, gravity and gauge theories, an infinite dimensional symmetry group on the boundary, roughly speaking corresponding to large gauge transformations and large diffeos at infinity. This may or may not be surprising to you if you've studied at all the BMS group and the asymptotics of solutions in GR. Maybe more surprising is the connection to this infinite dimensional symmetry group and the soft theorems. So the claim of Strominger and friends is that the ward identities for these symmetries are literally the soft theorems and subleading soft theorems that we know and love in scattering amplitudes. So I find this to be a very interesting connection because we usually think of soft theorems and ward identities in the context of pions, but now we're talking about gauge bosons and gravitons. Now, it's a very general statement. It applies in QED, angles, and gravity. So there's no restrictions on SUSY or anything. It seems like a very general set of facts. So the 2 points here are that it's an infinite dimensional space of symmetries, and two, that there's a connection to the soft theorem with respect to the ward identities. Now, what do I mean precisely? So we've seen this formula many times now, but there's the usual canonical leading Weinberg soft factor. Here it is for QED, and I'm just showing it to you to tell you that my notation will be that epsilon and k correspond to the polarizations and momenta of some soft particle. And of course, this has some universal form, just because it corresponds to long distance effects where there's some hard process which is a source for some long distance radiation. But we all know this well and good. Now, what is the infinite dimensional symmetry? What's the parameter of this infinite dimensional group? Well, it corresponds to the fact that when you have a particle emission, you can emit in any direction in the celestial sphere. Okay, so roughly speaking, Strominger's statement is that you can emit anywhere, and at any given angle, there's some current associated with that emission in the direction of that gauge boson or graviton. Now, that's a very beautiful story, but there are some caveats and some fine print, which I think are worth discussing. So one is that when we talk about the soft gluons, for instance, there's a stipulation, which is that they can't be any old helicity, so for 4 dimensions, you have to pick only plus helicity or only minus helicity. Okay, so from a pragmatic point of view, this is very natural because soft limits don't commute if they're opposite helicity, but they do commute if they're the same helicity. So it's not even clear operationally what you'd mean by soft limits of pluses and minuses. You'd have to make up some definition for that. Now, it's not at all clear to me within the construction of Strominger and friends why that was an outcome. It seems more like something added in post so that we can actually make sense of things, but it's some extra little rule that's added, as far as I know. The second caveat has to do with higher loop, where people in the audience computed the loop corrections to the soft theorems, the subleading soft theorems, which should be some ward identities of some symmetry, but they found that these soft theorems are anomalous. So they're renormalized, they change, which becomes very confusing if these are ward identities which should hold. Okay? So you could say that maybe they're violate or they're anomalous, but the fact of the matter is that, at least in my mind, there isn't a clear reason why these caveats exist, and in part that suggests that there isn't a complete understanding of why they worked in the first place. So I asked you, why did it even have to work at tree? Why did it have to work when I restrict the plus helicity. So the kind of point here is that we're in the situation I think we've all been in, where you have the instruction manual, someone who knows what they're doing can tell you step by step what to do, and at the end of the day you'll have a beautiful IKEA armoire and you'll be very happy, but you have no idea what those instructions mean or where they came from. Okay? So what you do in this circumstance is throw out the manual and find a friend and then try to come up with the rules yourself. So this talk is going to be about essentially trying to understand every aspect of what Strominger said about infinite-dimensional symmetries, the soft theorems, and also electromagnetic and gravitational memory effects from kind of a different direction, just a different standpoint. So the goal is to actually elucidate the origin of these symmetries from our own perspective. But to do that, we want some tool which will not be subject to choices, dials, or freedoms that we'd have afforded to us to kind of write down the right answer. We want something that just mechanically tells us there has to be some symmetries like this, they have to be connected to the soft theorems. So our approach is, in short, to apply the ADS-CFT dictionary to Minkowski space, to flat space. Okay, so this should already get you worried, just that statement. The usual way that people have discussed this is to take ADS and then take the limit as it approaches flat space. That's not what I'll be doing here, and much of what I'll talk about is about elaborating on this approach. But the final statement will be that we have an explicit step-by-step construction, just following the rules of ADS-CFT, where we can actually understand the connection between 4D amplitudes of gauge and gravity theory and a two-dimensional CFT. So what is my starting point here? What's the setup? So if you think about there being a hard process, hard scattering, it actually naturally gives you an origin of space-time. Okay, you imagine there's some hard process that's happening in short distances, all the soft stuff just sees this as some special point. So there's a natural foliation of flat space. Okay, so we're in Minkowski, I just want to cut up space in a very specific way that makes that origin point special. So the most natural way to do that is to just foliate space according to proper distances from the origin. So I call this proper distance e to the 2 tau. And this defines a subspace within 4D Minkowski, which is Euclidean ADS3, in this case of the forward light count. On the space-like separated slices, you'll get Lorentzian ADS3 slices. Okay, so all I'm doing is taking flat space and chopping it up into hyperbolic slices, each of which is an ADS3. Now, as you might imagine, these ADS3s are where we're going to apply blindly the ADS-CFT dictionary and see what we get. Okay? Now, to set the stage a bit, let me define the coordinates. So, of course, these are the usual Minkowski coordinates. I'm going to define Milne coordinates, for instance, in the forward light cone, which are the usual coordinates for Milne universe. But the point here is I'm engineering things so that I can just apply the dictionary as dumbly as possible, where I have I have coordinates tau, which is the proper distance from the origin, and then rho and z bar. Okay, so rho here, by construction, is the ADS radius on a given fixed tau slice, and z bar parameterize the boundary of the ADS3. Okay, so this is like just the point-wise coordinates of ADS3 by construction. Now, so just to orient things, so we should think of dd tau, Milne time translations, as kind of a proxy to time translation. Rho is going to take us along surfaces of constant proper distance from the origin. And then there's some 2D boundary labeled by z and z bar, which is literally the celestial sphere. So these are just angles on the sky. Okay? So that's, of course, where the CFT is going to live. Now, just so we can orient ourselves, imagine taking a position and just sending rho to 0, corresponding to approaching the ADS3 boundary. You find that this thing approaches a like vector, k mu, where k mu is conveniently precisely CP1 spinor helicity variables. Okay, so this wasn't by construction necessarily. All we did was use point Curie patch coordinates of the ADS3 slice, and we get these spinor helicity variables where lambda and lambda tilde are CP1s. I'll introduce these because I'll use them later. We can define polarizations for plus and minus helicities, which are just simple derivatives of the original form momenta. And the associated reference spinors are eta and eta with a bar. Now the usual Lorentz invariants that we're used to, angle brackets and square brackets, are just differences of z's and z bars. And this will be important later. The Weinberg soft factor is just 1 over z minus Zn, where Zn is the location of some hard particle on the celestial sphere. Okay, good. Now, so we set the stage. Now, you could immediately ask a question, because I said I want to apply ADS-CFT to slices of flat space, but there's many slices, right? So which slice do I want to apply this dictionary to? There's one for every value of tau. Now, the thing to do is just not debate or try to figure it out. Just compute something in ADS-3 CFT duality, and then interpret that in the 4D theory. Okay, so the idea is take an ADS-3 theory, think of it as being embedded in some unknown Minkowski 4, and then just ask what that means in that space. So let's just do that in the case of gauge theory. So the simplest thing you can compute in the dictionary is the bulk boundary propagator, which corresponds to taking some source on the boundary, labeled at some point ZZ bar, and letting it propagate into the bulk at some point x. Okay, so this is just a picture of the 3-dimensional bulk boundary propagator of some disturbance from boundary to bulk. Now we can just compute Ki, okay, so something you can calculate, it's trivial, and then you can lift it to Minkowski space, and I'm going to work in a temporal gauge where k tau is 0. And it's just an exercise I won't go through, but you get this expression, and you realize that this thing is actually a total derivative. Okay? So in 4D, the bulk boundary propagator is d mu of this factor, which should already kind of ring a bell, because as I mentioned before, the asymptotic symmetries discussed by Strominger and friends have a link to large gauge transformations at the boundary. So there's two things I want to emphasize here. One is that it's a total derivative. The second thing is that it's independent of tau. So tau, recall, was kind of the overall scaling of x, and this thing, it's x over x, so it's tau independent, which means it's Milne soft. Okay? So that's just another way of saying it's a zero mode in the tau direction. So kind of without any input, we've discovered that soft is somehow special in this picture. Soft is an output. We've learned that soft is important, and in fact we can go farther. So how do we go farther? Well, let's compute an actual Witten diagram involving this bulk boundary propagator. Okay? So here k mu is the bulk boundary propagator, and j mu corresponds to the rest of the Witten diagram. Okay? So we turn the crank, plug in that expression, and then we integrate by parts. And what we find, well, you have d mu j mu, which we normally say vanishes because currents are conserved. But you should keep in mind that that's not quite true, because there are hard particles that are actually produced at infinity, which are now scattered. Okay? So strictly speaking, on the boundary where other states are inserted, the current isn't conserved, which means that d mu j mu actually has delta function support on the boundary where you insert all the hard particles that are scattered. Consequently, this is not zero, and formally we can just plug in for that set of delta functions in d mu j mu and get this expression here. Okay? So you'll recognize that when xn approaches the boundary, so xn is literally where you have inserted a hard particle, xn, of course, approaches kn, where kn is the momentum of a particle. Right? The tau dependence cancels, and this thing is just epsilon.kn over k.kn, which is literally the Weinberg soft factor. So the point here is that the bulk boundary propagator, the bulk boundary propagator that you put in the Witten diagram, is equal to the Weinberg soft factor. Okay? They are equal. Which is, of course, strongly suggestive. It tells you precisely what the identification of state should be. Indeed, so the correspondence is that the Witten diagram is exactly the leading soft theorem. That's an equivalence. If you just simplify this in terms of the variables I used, you'll recognize that this is exactly the form of the word identity for a 2D conformal field theory. That's not a coincidence, because we started with a Witten diagram in ADS-3. Okay, so this is just a check. We determined that all of these things are actually the same: the soft theorem, the CFT word identity for conserved current, and the Witten diagram. And consequently, we know the identity of what that current is. The current corresponds to a soft gluon in the 4D theory. Okay? So the signs of this were abound in earlier literature, but this, as far as I'm concerned, is actually a derivation. Now, where does this leave us? Well, we know that there's a gauge theory. There's an ADS gauge theory. Well, what's the character of this gauge theory? What's the gauge theory? What is it? Okay. Well, we already have some clues, which is that the bulk boundary propagator is pure gauge, right? So it's something topological. It has no dynamical degrees of freedom, What's a three-dimensional gauge theory with no degrees of freedom? Well, the obvious answer is Chern-Simons theory. But you can actually just check this. So take the bulk boundary propagators, or any propagators, and just study them as solutions to some equation of motion. And you can inverse derive that these are actually solutions to a Chern-Simons theory. But there's kind of a shortcut to this, which I want to go through just because it's maybe a little bit faster, which is consider the following. Take an amplitude that only has positive helicity soft gluons on the boundary. Okay, so the idea is I want to kind of factorize all the degrees of freedom into soft stuff and hard stuff, where the hard stuff is some background which sources the soft stuff. Now, the soft stuff, if I restrict to strictly positive helicity, will by construction satisfy a self-dual condition on the boundary. So I think if this is a Cauchy evolution problem in some hard background, then this self-dual condition will be preserved as I integrate into the bulk, right? What that means is that effectively, even in the bulk, the self-dual condition is conserved. That's just the statement that self-dual solutions still satisfy the Yang-Mills equations. In which case, I can treat the self-dual condition as something that's true in the bulk. You can plug this into the action, and then you get that this goes to FF tilde, which is a total derivative, topological theory, which limits to precisely the Chern-Simons action. Okay? So here I've crucially used not only the choice of gauge, but also the fact that I was only considering soft, Milne soft particles. Okay? But the upshot here is that the massless vectors in ADS3, the guys that we were computing the bulk boundary propagator for, they correspond precisely to a Chern-Simons theory that describes single helicity modes of the 4D, single helicity soft modes of 4D. Okay? Now famously, this Chern-Simons theory has a dual itself, which is the Western-Witten model in 2 dimensions. And this is the full correspondence. So some subset of the 4D Yang-Mills theory is soft gluons of a given helicity. We can map this directly onto the Chern-Simons theory, which through the second duality down to 2D is given by the Western-Witten model. Now famously, WZW has an infinite-dimensional symmetry, it has a Katz-Moody current algebra, given by some JZ. The generators are just simply given by the Laurent expansion. And this is precisely the Katz-Moody that was kind of seen by Strominger in his manipulations of the amplitudes and his asymptotic symmetries. It's the same one, except there's a cute, this derivation shows you directly the connection between this and the Weinberg-Saw factor. So we think of this normally as just the OPE of conserved current with some operator, which is the hard stuff. But this is, again, also just the Weinberg-Saw factor, if you look at it in our coordinates. Okay? Very good. So, what does this mean? Well, the Western-Witten model is very constrained, right? It has extremely stringent constraints on correlation functions. So in particular, you could ask, what if I take some hard particles and just take a string of conserved currents, JZ1, JZ2, etc.? Well, that should give you a very constrained structure that is implied about scattering amplitudes. In particular, it tells you that if you take some hard states and then add a whole bunch of soft particles, where here I'm in color order, then there should be a fixed holomorphic structure to the amplitudes. It should be holomorphic just because JZ is holomorphically is conserved. Okay? Now, what that means is that when you take multiple soft emissions of fixed helicity, then the objects you get should be purely holomorphic, and in particular, they should come in these MHV denominator strings. Seems like a strong constraint, but of course, if you think about it for half a second, you realize from amplitude's point of view, this is totally obvious. Just take a consecutive soft limit of 2 and then 3, or 3 and then 2, and they're the same, and it gives you these types of MHV strings. Okay, so this is an innocuous fact about scattering amplitudes in the multi-soft limit, but it has a different, there's an originating reason for this, if you think about this from the point of view of the CFT. Now let me mention something about electromagnetic memory, because this is actually a cool story that was also discussed in depth by Strominger. And it boils down to another kind of pillar of his discussion, which is that you can study something called the electromagnetic memory effect, which is the following. So imagine you put on the sky a little circle, a disk, which I'll label by R, and you do the following experiment. You integrate over all times, and just integrate over all the electric charge that flows through that circle. Okay? So I'm just integrating through some surface ds, the current to Ji over all times. So this is called electromagnetic memory because it's over all times and it's just recording the charge. It's doing nothing more than that. It's like the LHC detector. Now, through some manipulations, you can apply whatever the Ampere's law to rewrite this in terms of the B field. Okay, so now it's a line integral around this circle. For the case of particle radiation, where we have self-dual radiation, because it's either positive or negative helicity, in which case we can rewrite the B field as I times the E field, which is in turn the tau derivative of AI, the gauge field. And AI, we can eat up this tau derivative with this tau integral to just give us the value of AZ at the end of time. Okay? So what you end up getting for this electromagnetic memory effect is essentially an Aronoff-Bohm circle at the end of time, encircling some little circle R. So that's morally speaking what this, it's what this electromagnetic memory effect is. But what's cool is that this has a direct interpretation in the CFT. Because we know that A of Z is just the boundary gauge field. That corresponds, is dual to the current in the CFT. And this object, this Aronoff-Bohm phase, is literally a generator of Kac-Moody algebra. So this is a new way to think about the Aronoff-Bohm phase in terms of the 2D CFT. Okay, so this is the full dictionary between CFT and Yang-Mills. Conserved currents are soft gluons. Other operators that are hard are other operators that aren't conserved or hard gluons. But nonetheless, they participate in the OPE, so you know that they live in the CFT. So in some sense, this is the most striking thing. We understand the conserved currents and the soft gluons the best, but everyone, even the hard particles, are participating in the OPE. So somehow there should be some purely CFT way of describing all the degrees of freedom. And this is, of course, the most exciting possibility. The infinite dimensional symmetries are just conserved current in the CFT, and these memory effects are just generators. Okay, so that was it for gauge. I feel like I should talk about gravity because it's equally interesting. I'm not going to go through all the details of the calculation, but you can do exactly the same thing. Again, there's no freedom. You just apply the dictionary totally mindlessly and see what you get. Here, the bulk boundary propagator for a tensor in ADS3 is given by this, if you use the embedding formalism from before. Notice, curiously, that this thing has the form of a double copy of the gauge case. I'll leave that to you to decide what that means. It's also a total derivative. Okay? So it's also pure gauge, just like in the case of gauge theory. And we just repeat our earlier procedure. Okay? So compute the bulk boundary propagator, see what it means in 4D, and you find the following. So you imagine constructing a Witten diagram together with some stress tensor. You find after some calculation that this is related to some kind of bizarre convolution of the subleading graviton soft factor. In fact, precisely as Strominger's directions say. So one thing you should keep in mind is that Strominger has never said that the subleading soft factor is literally the word identity. You have to do some manipulations of the subleading soft factor in order to produce the stress tensor in his mapping. Here we have just derived it, and it's manifestly the subleading piece. It looks a little bit scary, but if you just simplify it, you'll see, well, I won't go through it, but this thing is equal to the following expression, which is the CFT, the well-known structure of a CFT word identity for the stress tensor of a two-dimensional CFT. Okay, so this is the one-pole term and the double-pole term, where now we can interpret this operator essentially as the thing that extracts the conformal weight from any given hard particle. Okay, very good. So we now have a relation between, not just between the generators here, but also we can ask about gravitational memory. Okay? So this is another thing that Strominger talked about. Roughly speaking, gravitational memory is the fact that you can take a bunch of test particles and put them like on the boundary of space, and when gravity waves pass by, they end up displacing those particles in various ways. Okay, so much like the E&M memory effect, it's kind of like a DC effect on test particles that you put in infinity. Now here we can again just analyze our formulas for the stress tensor and expand T around, let's say, some arbitrary point and extract the SL2C subgenerators of the Virasauras living inside TZ. Anyway, TZ is the stress tensor of a 2D CFT, so it has some Virasoro algebra, much like the Kac-Moody algebra. And we can just look at the SL2 subgroup and study what that is. Okay? Now what's cool is, if you do that in this exercise, you'll see that the three generators of SL2C just correspond to boosts and rotations locally around the hard particle. And so there's a really physical picture that has emerged, which is that if you take a soft graviton, which is nearly collinear with some hard guy, it effectively just rotates him or boosts him. Okay? So it gives you this picture familiar from SCET, which is that there's some reparameterization invariance which corresponds to a local boost, which wiggles your hard legs whenever there's a graviton that's emitted collinearly to it. Okay? So this actually dovetails nicely with some things that some SCET people were thinking about in terms of this connection. In terms of the gravitational memory, we can do exactly the same procedure. As you might imagine, you just put a circle here, you measure the gravity waves that come out, you apply a bunch of identities, but you find that precisely the thing being measured is just a local boost, which is the Virasoro generator. So in the case before, we had that E&M memory was a Kac-Moody generator of the 2D CFT. Here, these gravitational memory effects are connected to Virasoro. Okay, I think I went really fast, but that's okay. So here are my conclusions. First, we proposed explicit duality between 4D gauge theories in flat space and a 2D CFT living on the celestial sphere. The properties of this CFT are that collinear singularities on the sky are the operator product expansion. Moreover, just by applying ADS-CFT mechanically, using a hyperbolic foliation of flat space, we can map the soft gluons and gravitons onto conserved currents. And literally, the soft theorems are CFT word entities. They're up to these convoluting integrals that I showed you before. And finally, the Kac-Moody and Virasoro generators are precisely the infinite-dimensional symmetries that were observed, and all the memory effects are just these generators. Now, in terms of future directions, there's of course the question of translating every possible thing we can think of in ADS-3CFT2 into 4D flat space and just asking what it is. We want to test this correspondence. We have a lot of evidence that something is happening, but the thing to do is just check everything we can. And the great thing is that it's connected to scattering amplitudes in 4D, so we can actually check things. One thing we want to do, which I didn't discuss at all, is construct the operators not just for soft modes, which are the conserved currents, but also the hard modes. So I didn't go through this, but we have a direct mapping between hard gluon modes, superpositions of hard gluon scattering amplitudes being equivalent to certain operators in the CFT. And these are not conserved currents, these are just other operators. But just understanding this full picture, how they participate in the OPE, etc., I think is one of the clear next things to do. Of course, the kind of elephant in the room is all those questions I mentioned before, which is the caveats. And fortunately, in everything I've discussed, I can point to you precisely where I assumed tree or I assumed fixed helicity. But now that we know where we input those, we can try to relax those assumptions and ask what changes. In particular, for the case of higher loop, and since this is kind of a point of contention, I think I'll maybe elaborate on a bit. It's simply a fact that the subleading soft theorem is anomalous at one loop in the sense that it's not of the same form as a tree. But as I showed you before, the stress tensor isn't literally, the CFT word identity isn't literally the soft theorem. It's a soft theorem together with some convolutions which can shift around singularities and do all kinds of funny stuff at higher loop. So one thing we can just do is just take the higher loop expressions and just check after our mapping whether it's maybe not the same form as it was for the subleading soft theorem, but maybe it could still be a conservation word identity for the CFT. And of course, maybe the most ambitious thing we could try to think about is information paradox, but I have not much to say about that now. Okay, that's it. Thank you.
We have a question up here.
So does the Cheung-Simons level ever come into play?
That's a great question. So it's kind of amusing. So in this picture, the level is like the first thing you would ask about if I was starting from the CFT, but it's much harder to see in the 4D theory. It's so hard that if you read Straumer's papers, he's oscillated between it being vanishing or the gauge coupling, depending on what the question you ask. But I think we can evaluate this question because you can extract the level basically by studying diagrams where there's some hard process, a soft emission, and then absorption into another hard process. So the level's related to the gauge coupling, in the case of the gauge theory, and it's related to G Newton in the case of the gravity. Yes. But yeah, that's what it would be. Now what that means when you renormalize it at one loop, I'm not sure yet. but that seems to be what the theory is telling us.
So I had two questions. The first one was about the Virasol that you found. What's the relation between it and asymptotic symmetries of flat space?
So I would say that, there's a mapping between the Virasora generators and the BMS. So I think you're asking about the super translations and the super rotations and how they're
Effectively, super translations are not Virasora.
Yeah, exactly. Good. So I can even show you where you see that. So if you look at, so there indeed Virasora is the super rotations. The reason why you can see the rotations show up is just in this expression, the fact that J mu nu, rotations on infinity, enter. If you want to construct the rest of the BMS algebra, you would just commute TZ with a translation, and you can build the rest of the super translations and just check that they have the right properties.
If I remember correctly, there were some problems with defining the finite charges for super rotations. Like if you try to actually exponentiate those generators, you would try to do this with symmetric groups, and it doesn't really work. Somewhere.
I don't have any comment on that, but we haven't seemed to have any issues dealing with it yet, but there could well be settled.
Linearized treatment.
Sorry?
This is a linearized analysis.
So some of it's linearized, some of it isn't. So the Yang-Null story I talked about, you had a multi-soft emission. We're trying to understand the gravity case for multi-graviton emission, and I'm certain that for fixed helicity graviton emission it will work perfectly fine. So indeed, part of the value added is to study this in the nonlinear regime, and I think in the gauge theory case we have worked that out entirely.
I agree with that.
Yeah, for gravity we just need to think more, but I don't see any obstruction to it currently. But we'll see. Yeah.
The second question I had was about this dictionary, reducing everything to Euclidean ADS3 and then using ADS3. There seems to be an effective reduction to 3 dimensions, as you said, for the soft particles, but if you actually consider propagating
Right.
Minkowski, then you have to do a reduction along the pattern.
That's right.
And that seems to give some sort of non-local structure.
Right, so the way you would see this is you can take these Milne slices at different tau and do a mode expansion in tau, in which case the modes that are non-zero modes actually correspond to objects with conformal weight different than 1 or 2. So we have worked that out. I didn't show it to you now, but in this discussion of the mapping between hard scattering amplitudes and operators in the CFT, we do this explicitly. So indeed, it's something you have to be careful with. You have to do a mode expansion and study the ADS3 theory in some sense like a Kaluza-Klein reduction, where you have KK reducing. Yeah, so you have to, it's a little tricky because of the continuousness of it. So if you really had an infinite space, tau max goes to infinity, then there's some subtleties of the order of limits, which I think is crucial. But let's say I just fix an end of time, then I can at least put it in a box, and that's the simplest case we're studying.
Any question over here?
So when I think about the double copy or the solve theorems, they're very deep, independent, but you seem to be very stuck in 4 dimensions. Do you have any comments on that?
Yeah, so I think that's the reason why I'm not going to claim that I know how any of the double copies work. I should say everything I've done, even though I jumped to 4D very quickly so that I could have more, could do more. We can of course do this in general dimension, right? This picture of just a point, foliate, get ADS D-1 slices, that's very general. For the particular question, the double copy, I'm certain this is actually related to your work, precisely your work on this, because I'm talking about a mapping between self-dual sectors of gauge theory and gravity in 4 dimensions having a double copy structure. In fact, one thing I did mention was that in the case of the gauge theory, there's this famous fact that the generators of the current algebra, if you square them, you actually get this contribution to the stress tensor through the Shugawara construction. So it definitely smells a lot like a double copy piece. It's super 4D, but we haven't looked outside of 4D almost at all. So I don't know if it reports it doesn't, but certainly I think it connects to your work on self-dual double copy. And definitely there's some connection there.
I was wondering if you've looked into or could comment on
extending it, adding supercharges to Yang mills and seeing what happens to these. And for n equals 4, it should allow you to relax the Felicity.
Right. I think I don't see any obstruction to doing that. I think it would work beautifully. Yeah, I put that in the one of our many things we need to do. But yeah, adding SUSY I think won't be difficult. I don't think it would change the story much. It would add some additional structures, and it'd be interesting to see what those word identities mean in 40. But I'm certain they'll just be the supersymmetric versions of all the soft things. But that's certainly what you list.
Maybe the last question.
Does this ADS 348 all the entire Minkowski space, or just a patch of them?
That's a good question. So I only showed you the middle foliation, which is the forward and backward light cone, if you like. There's also there's regular foliations, which are exactly the same except for signs. What's great about this embedding formulas of these prop years I showed you is that they automatically analytically continue between all of them seamlessly because there's no actual artifacts. I mean, it's a coordinate artifact that they're split. So everything I showed you doesn't need to care about the difference between the middle and real wedges. But indeed, if you want to foliate it, be careful with everything you have to include it.
Another question, related question is that just now I got a bit confusion because if I remember correctly, in the story that Strong inference had, it need a sort of unipodal identification between the infinite past and infinite future.
Right.
And is there some counterpart in your story, or you actually don't need this?
So I don't quite see where that is. I think partly because I'm like doing all-in formalism for scattering up to that maybe just sidestepping that. But I think there's definitely some subtlety to that, which we may just be eliding. And here's what I mean by that.
I know that people are confused about that condition or not.
Yeah. So for instance, for the gauge theory case, I don't think it's crucial to understand it because you can imagine the gauge theory case taking some neutral and letting it like a Higgs and just let it propagate to the origin and decay, and I can just imagine only final states. But for gravity, of course, you can't do that because the stuff that comes in is charged under gravity. There could definitely be some subtlety in that. We're not seeing it yet, but well, if you do more calculations, you'll be able to rise.
But at least could you make some suggestions on how to understand this? Do you have some comments?
I need some time to think about that. I'm not sure. Like we haven't encountered any pathologies like this, and I understand it was a big. That's like one of the sticking points in the original analysis. It could be that we're somehow blind to it, or we have to do the right calculation to see it. But I'm not sure yet.
Thank you.
Okay, so let's thank Clifford again. Don't go away because there are now some practical comments.
First of all, I'd like to advertise next year's meeting.